Let's practice calculating formal charge. In this problem from your book, we're asked to do a couple of different compounds. I will say that I skipped one, so what I have listed as B here might be C in your book. But if you want more practice, E and H in the same problem are excellent ones, and the answers are in the back of the book so you can check your work. Let's start with this very first one. This first one has a little bit of a kink in it because we have one phosphorus and one oxygen, so we have to do something else to determine which one is our central atom. What we have to think about is the number of bonding sites. Phosphorus has 5 valence electrons, so that means that it has 3 unpaired electrons, and thus 3 what we would typically think of as a location for a bond. Oxygen, however, has 6 valence electrons, so it only has 2 bonding sites. So our phosphorus is going to be our central atom. We know our chlorine has 7, so let's draw those 3 chlorines real quickly. And hopefully, at least the chlorine bonds are very clear. Those unpaired electrons pair up immediately. Now with this oxygen, 2 different things could theoretically happen. Each single electron, they could split apart this unshared pair and create a double bond, but that's not going to happen because of this line right here. We can't put more than 8 electrons on that phosphorus. What happens instead is this one scooches over, and this previously unshared pair becomes a shared pair. This results in phosphorus single bonded to 1 oxygen and 3 chlorine atoms. Now to calculate our formal charge, we do number of valence electrons on the neutral atom minus the number assigned to it in this molecule. To count the ones assigned to it in the molecule, each unshared electron is counted, but for every shared pair we only count one of the shared electrons. So for example, phosphorus had 5, but now it has 1, 2, 3, 4. So 5 minus 4 gives us a formal charge of positive 1. Oxygen had 6, so now it has 2, 4, 6, 7. 6 minus 7 gives us negative 1. Chlorine had 2, 4, 6, 7. 7 minus 7, all of our chlorine atoms have a formal charge of 0. It's important if the atom or the molecule is neutral to make sure that your formal charges equal out to be neutral as well. In this case, they do. Let's look at B. In B, we've got a charge, so our formal charge needs to add up to negative 1. In this case, we have chlorine in the center, which is a little awkward since it already has 7 valence electrons, but we'll make it work. And our oxygen atoms all around the outside, because there's 4 of them. So one bond is easy, and we have this. So that means we've got an extra electron. I'm just going to draw it there. So that oxygen is happy. Both, or the oxygen so far is obeying the octet rule, so that one's good. In order to make these oxygen atoms obey the octet rule, as well as the chlorine, we're going to shift that over and share our previously unshared pair for all of them. We end up with a chlorine single bonded to 4 oxygen atoms. And our compound has a charge of negative 1. If we count our formal charges, chlorine had 7, so 7 minus 1, 2, 3, 4 gives us positive 3. Oxygen has 2, 4, 6, 7, so 6 minus 7 gives us negative 1. because this is the same. They're all going to be -1, which gives us a total charge of -1 to match the charge on our compound. Let's do one more example. C was PO4, -3. It's the phosphate ion. Phosphorus is going to be in the center. And we're going to have an oxygen atom on every side. Because we've just been doing it a bunch, hopefully we see that that shifts over and this unshared pair comes in. We have to remember we have -3, so that means we got 3 extra electrons in here. Let's put one on each of these, and then we can see that that bond also forms. So we have our phosphorus single bonded with 4 oxygen atoms. And this compound, or ion, has an overall charge of -3. And that would usually be in the upper right-hand corner, but I'm kind of got other stuff in the way, so. Let's add it up. Phosphorus had 5, so 5 minus 1, 2, 3, 4 gives us +1. Oxygen had 6, and now it has 7. So -1, -1, -1, -1. This is very similar to the previous problem, just with a bigger negative charge. So we have +1, add up 1 positive, 4 negatives, we get this charge of -3. Let's apply this formal charge in another way. This problem is a great way to apply formal charge. It's asking you to look at all the possible non-equivalent structures for this compound and use that formal charge to decide which one is the most appropriate and the most likely to be correct. These structures are not going to obey the octet rule, just as a heads up. Xenon is a noble gas, so it has 8 valence electrons. And we've got 3 oxygen atoms. Well, I guess some of these will obey the octet rule. We just talked about on the previous problem how this can happen with these oxygen atoms. Those scooch over. Now we get xenon single bonded with 3 oxygen atoms. And let's come up with all 4 structures before we do formal charge. But we had also talked about what else could happen here. We said that the xenon could have these unshared pairs split up. To create a double bond. So we could have like this. And this could happen with every oxygen atom. So we could also have xenon double bonded to 3 oxygen atoms. And I don't think we need to draw any more structures from scratch, because the other 2 non-equivalent structures are what happens when we mix some double bonds and some single bonds. So in one of them, we can have 1 double bonded oxygen atom and 2 single bonded. Now there are two resonance structures of this that we're not going to draw because they're equivalent. We could have the one double bond here and these both be singled, or one double bond here and these both be singled. So that's what we mean by non-equivalent, not resonance structures of each other. The last one occurs when we have two double bonded oxygen atoms, and they could be any two. I like the symmetry of them being the ones across from each other. So that's how I drew it. But again, that would be a resonance structure, depending where you want that single bond. Let's talk formal charge for these now. Xenon has 8. So we have 8 minus 1, 2, 3, 4, 5, 6, 7. So 8 minus 7 gives us positive 1. And oxygen has 1, 2, 3, 4, 5, 6. 6 minus 6 gives us 0. So we know double bonded oxygens are 0. 2, 4, 6, 7. So 6 minus 7 gives us negative 1. So that one's pretty good. In this one we have xenon 1, 2, 3, 4, 5, 6. So 8 minus 6 gives us positive 2. We know our single bonded oxygen atoms have a minus 1 charge, and all double bonded ones have a 0 charge. And plus 2 and 2 negative 1s give us a neutral atom. In this case, we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 8 is 0. There is no formal charge there. And we know double bonded oxygens have a formal charge of 0. So hopefully you know right away that this is the appropriate structure because all the formal charges are as lowest as possible. But let's go ahead and double check here. So 1, 2, 3, 4, 5. That gives us plus 3. So this one is the least likely because it has the highest formal charges. This one is the most likely. And this one is the next most likely. Because they always want to have the lowest formal charge.